So we have here a problem with static equilibrium and torque. So this long stick here, this rod, is meant to represent a human arm. Just to keep it simple, we'll treat it as a thin rod. And we're told that the mass of an arm is 14 kilograms. And it has a length of 76 centimeters. Right, so the entire distance is 76 centimeters. And the arm makes an angle of 42 degrees below the horizontal. Okay, that means that if I consider this angle here, this angle is also 42 degrees. Right, when you got two angles like this, we call those interior angles. If you connect two parallel lines with a straight line, then you get interior angles like this, and those are parallel. Okay, so we're told that the shoulder exerts a horizontal and vertical reaction force. So somewhere up here, there's a horizontal and vertical reaction force. So there's our horizontal reaction force, and I'm going to draw the vertical reaction force pointing up. I actually don't know which way it points. It could point down, but I'm just going to guess for now that it points up. Okay, so let's consider the forces acting on the arm. Gravity, certainly. There's mg here, which is halfway down the arm. And then there's this tension here. I haven't necessarily drawn this to scale, but there's a tension here that is 16 centimeters down the arm. Okay, and that's going to be too messy to try to draw all those distances in. And we've got horizontal and vertical reaction forces. There aren't any other forces acting on the arm at this point, right? So, of course, my sign convention is going to be that my standard Cartesian sign convention, that to the right is positive, up is positive, and counterclockwise is positive. So, let's start with our forces, right? So, the sum of all x forces. There's a horizontal force, and then there's this tension force. All right, so if this angle is 42 and this angle is 13, then those two angles combined add up to 55 degrees. So I can write the tension, the component of the tension that's in the x direction is Ft cosine 55, and it's negative because it points to the left. As far as the y forces are concerned, I've got the vertical force. I got Ft sine 55, that's positive because it points up, and then I got minus mg, and that equals 0. Alright, now for the torques, I'm going to, my strategy is always going to be to put the pivot where the most unknowns are, and I got two unknowns there at the shoulder. So, sum of all torques is going to be the torque due to tension plus the torque due to gravity, because the torque due to the horizontal force and the torque due to the vertical force are 0 because they are located at the pivot. So let's consider first the torque due to tension. So it's going to be the tension is making the arm rotate in a counterclockwise direction, so it's positive. The distance from the shoulder to the point of application of tension is given in the problem statement to be 16 centimeters. Tension force is unknown. And then sine, okay, so the r vector points down like this. And so we got to consider this angle here, which is 167. Okay. And then the torque due to gravity, well, gravity is making the arm rotate in the minus direction. Gravity is located, so we got to read the problem carefully, right? It says a human arm can be approximated as a uniform thin rod of length 76 centimeters. If it's uniform, that's telling you that gravity is located at the geometric center of the rod, which would be 38 centimeters, half the length. So that means our r vector has a value of 0.38. Gravity is just 14 times 9.8. And then here's our r vector, points down like that, and that makes an angle of 42 degrees, and so the angle here between gravity and my r vector must be 48 degrees. Sine 48. Okay? So my sum of all torques equation looks like this. 0.036 Ft minus 38.74 is equal to 0. So, I've got three equations and three unknowns. My three unknowns are Ft, which also appears here and here, Fh, and Fv. Right? Let's see, if I solve for Ft, that's, 38.74 over 0.036. So that works out to be 1,080 newtons, or we'll call that 1,100 newtons to round off. So there's my first result. Looking at the sum of all x forces, I get Fh minus 1080 cosine 55. Therefore, Fh is 620 newtons if I round off. I actually get 617, but I'm rounding to 620. And then for my y forces, let's see, Fv plus 1080 sine 55 minus 14 times 9.8. I get Fv is minus 740 newtons, rounding from minus 744. So what that negative sign means is that I guessed wrong about the direction that Fv points. Fv actually points down. So the vertical component of the reaction force there, Fv, is 740 newtons. It's in the minus y direction. Right. Fh is 610 in the plus x direction, and the tension force is indicated in the diagram. The horizontal force is indicated in the diagram as well, but I felt it was necessary to go ahead and clarify that Fv is in the minus y direction. That's all it asked for, so we're done.